Hello all and welcome to my channel. I'm very happy that I finally uploaded a long form video related to something else than physics yesterday, and it got a few views, but it's not that it took off. So that's a format I actually want to make. So it's one of the personal goals I have for the channel to kind of travel around, film these videos related to physics, but also film videos related to uh, things that I find interesting about various locations. Anyway, this is a paper requested by one of the viewers. It's one of the things I actually avoid doing because that, will make me feel like I'm being used by you guys. Okay, I mean, you are really great, but I don't want people to think that I can, do things on demand. I mean, okay, it's good to get some feedback from you, but I'm still not making a living from this channel, sadly. So, I mean, if I was making a living, it would be great. I could pump up videos, maybe 1 or 2 videos per day, especially about A-level physics, which is kind of easier for me. Because the actual goal is to upload more advanced physics material. But anyway, today we're going over Unit 1 paper, okay? So let's focus back to our task. This one is from October 2023. Again, it was requested by one of you guys. I'm not gonna say who. So let's dive in, I guess. I usually have an introduction where I say multiple things, but okay, let's go over the things I always say briefly. For the multiple choice section, usually 2 out of the 4 options are totally wrong. The dimensionality might not work, or the physics might not make any sense, etc. But sometimes 3 out of the 4 make no sense, especially if you check the unit. Okay, so have that in mind. The second thing, half the answer is in the question. What does that mean? That if you understand the question, then you will be able to answer the problem. Okay, if you don't understand the question, try to read part B of a question. So this refers to questions in section B. So they usually come in part A, part B, part C. Sometimes if you read part B or part C, it will help you understand what the question is actually asking in part A. Okay, it doesn't always happen, but it happens. The other thing is that you have 90 minutes to solve this paper, and it awards, I believe, 80 marks. Let me know if I'm wrong. We can actually quickly check. Okay, where is it? So yes, 80 marks. So try to spend a minute per mark. If a question awards 10 marks, try to spend 10 minutes. Okay, then long answer questions. Try to provide a sentence per mark. So if it's a 6-mark question, about 6 sentences. If it's a 5-mark question, 5 sentences, and so on. And use the spreadsheet that they give you with the formulas. Okay, it sometimes gives you inspiration about what you need to do. So okay, let's start. Question 1: a quantity is either a scalar or a vector. Which row of the table is correct? Okay, so option A says that energy is a scalar and momentum is a vector, which is absolutely correct. Okay, because momentum has a direction, energy does not. So that's correct. The other options are wrong. For example, you see that in option C, they have mass as a vector. Makes no sense, etc. So let's move on to question number 2. Which of the following is an SI unit for momentum? Okay, so momentum is P is mv. Okay, and if you put the square brackets, again, the square brackets mean the units for a quantity. Okay, then the units for momentum are kilograms times meters over second, which is option A. I want to say a word about my handwriting. Some of you complain, sometimes the comments are a little bit harsh. So I'm a little bit sensitive sometimes. But guys, I mean, as far as the physics is correct, the handwriting is not that important. I do my best. Okay, sometimes I forget to try. So I'll try to improve it, but hey, I'm 1,000 years old. What do you expect? Old dogs don't learn new tricks. But yeah, I hope the videos are useful nevertheless. So let me know what you think in the comments. Question 3. Which of the following could be used to describe the elastic limit of a material? So option A says the stress above which the material will not obey Hooke's law. That's the limit of proportionality, so no. B, the stress above which the material will be deformed when the stress is removed, which is exactly the elastic limit, okay? So let's read the other option. C, the stress at which the material undergoes a sudden increase in extension. That's the plastic deformation region. And D, the stress at which the material breaks. That's the breaking stress. So no. Okay, moving on. 4, a ball falls through air from rest. Which of the following shows the graph of displacement against time for the ball? Okay, first of all, option A, the gradient is 0, therefore the object is stationary, so that's wrong. Option B, the gradient is constant, meaning that it has a constant velocity, but it falls through gravity, so it's accelerated by gravity. And we have to assume that there is some drag force as well, so B is wrong. Now C is an interesting choice. Let's use the red color. So the gradient of the displacement time graph is the velocity, right? So notice that, okay, that's not good. So at time equal to 0, the gradient is about 0, right? So because it starts from rest. And then the gradient gives you the velocity, right? So the gradient keeps increasing because, the gradient keeps increasing because the velocity increases, right? So option C actually works, but let's see what's going on with option D. Option D has a non-zero gradient at time equal to 0, which means that the object has some velocity at time 0, which is erroneously wrong because it says that it falls through air from rest. Okay, so option C is the correct option. 5. The helicopter moves vertically upwards with an increasing speed. Which of the following describes the increase in gravitational potential energy of the helicopter? So A says the work done on the helicopter by the force of gravity. No, it's the reverse of that, okay? And we'll see in a moment. So B, the total work done by the helicopter as it moves upwards. It doesn't specify work against what. So B is wrong. C, the work done by the helicopter against the force of gravity. Okay, so that's exactly the increase in gravitational potential energy. Okay, so C is the correct answer. And then D, the work done by the helicopter to increase speed. No. Okay. And this work done, by the way, is mgh. Okay. So because it moves vertically upwards. Okay. 6. An object moves with a velocity v. The kinetic energy of the object is doubled. Which of the following is an expression for the new velocity of the object? So the kinetic energy is 1/2 mv squared. The new kinetic energy is 2 ke. So it's going to be 1/2 m, and let's call it v prime squared, right? And we know what the kinetic energy is initially. I'm going to use a clean page. Do we need it? No, maybe I'm going to come up there. So 2 times 1/2 mv squared, which is the kinetic energy, right, must be equal to 1/2 m and then v prime squared. So m cancels, 1/2 cancels. So we have that v prime is √2 times v, which is option A. I hope this makes sense. Let's move to question 7. A power station provides an electrical output power of 2.1 gigawatts. The power station transfers thermal energy to the surroundings at the rate of 3.4 gigawatts. Which of the following gives the efficiency of the power station? So the efficiency is the useful power, so useful P over input power, right? What's the useful in this case? It's the 2.1 gigawatts, right? So that's what we get out, okay? So a power station provides an electrical, it actually says it, electrical output, okay? So that's the useful output, the useful power, okay? So 2.1 gigawatts. The power station transfers thermal energy to the surroundings at the rate of 3.4 gigawatts. Okay, therefore the input is going to be the 2.1 gigawatts that is the useful output plus whatever is lost due to thermal energy transfer with the surroundings. Okay, so gigawatts cancel, and this is option, which option is it? Option A. Too many A's so far. So 1, 2, this is the third. So half the question so far had option A as the correct one. It's crazy. Don't know why. Okay, let's move on. Okay, question 8. A student applied a tensile force to a metal wire of length x and diameter d. The length of the wire increased by delta x. The student applied the same force to a second wire made of the same material. The length of the second wire increased by 2 delta x. Which row of the table could show the length and diameter of the second wire? Okay, I'm going to use a clean page because we will run out of space. So this is the wire, okay, and it has a length x and a diameter d. Okay, so we know that stress is strain times the Young modulus, right? So stress is force per cross-sectional area, which we write as pi d squared over 4. And this must be equal to the Young modulus times the strain, which is delta x over x. X is the original length, okay? So delta x, the original delta x, is 4 times f times x over the Young modulus times pi times d squared. Okay, so now delta x prime, the new delta x, will be 4 times the same force, right? Because the same force is used over the Young modulus, which is the same since it's the same material, times pi, and then times x prime over d prime squared, okay? And whatever x prime is and d prime is should give us 2 delta x, okay? So if we try, if x prime is equal to 0.5x and d prime is equal to 0.5d, then we will find delta x prime is equal to 4f over the Young modulus times pi, right, times x over 2 times d squared over 4, okay, which is exactly 2 times delta x, okay? So this option doubles the extension, and I took this option from option A, okay? In case you're wondering, I didn't just think about it, okay? So option A actually works. And if it wasn't for option A, you should have tried option B, but option B tells you that the diameter is 2D, which means that it's going to make the extension smaller, right? So you have to test those values pretty much to find the correct answer. Okay, I hope this is comprehensible. I mean, this is something you guys understand. So let's move on to question number 9. Okay, question 9. A box of weight W is suspended in equilibrium from a support by 2 ropes. The tensions in the 2 ropes are T1 and T2. Which of the following is a vector expression relating the forces acting on the box? Okay, so to add this, so basically when we have equilibrium, the 3 vectors add to a triangle, okay? So if we parallel transport T2 and put it there, then we will have T2, and okay, I assume this is not to scale actually, so maybe this is a bad example, but that's the general idea. And then T1 will be, okay, maybe this is T1. We parallel transport it to the head of T2. Okay, let's make T2 a little bit smaller. So this is T2, oops. This is T2 and T1 and W, and they all add to 0. So T1 plus T2 plus W is equal to 0 because, again, they have to form a closed triangle for equilibrium. So that's option D. Okay, and finally, for section A, the last question is, a box is pulled along the ground by a rope inclined at an angle of 40 degrees to the horizontal as shown. The tension in the rope is 30 newtons. The box is pulled 5 meters along the ground. Which of the following is the work done on the box? So since the force makes an angle of 40 degrees, we have to resolve it and analyze it into a horizontal component, which is going to be 30 times cosine of 40 degrees times, newtons. And then the box, let me make that go away. Sorry about that. So, I mean, there was a thing that popped up in the bottom. It's something that tries to translate whatever I'm writing. So I guess you guys are right that my handwriting is so horrible that the system doesn't recognize that it's English. So anyway, so that's the component of the force that does work, because the other component is this one, which is 30 sine of 40 degrees, but it's perpendicular to the displacement, so it doesn't do work. Okay, so the work done is simply this component times the distance, the displacement. So 30 cosine of 40 times 5 gives you 114.9 joules, which is most close to option B. Okay, so this was section A. We are ready to move on to section B. Okay, section B, question 11. The photograph shows a rocket. This rocket is launched vertically, and the source is from NASA. So these are not good rockets, guys. Only Elon Musk claims to have the perfect rockets. But NASA buys from Elon Musk. I think they do. So yeah, this is a joke, by the way. So I don't know what's going on. So, okay, question A. The rocket's engines give a total upward thrust of 7.3 times 10 to the 7 newtons. That's a huge force. Calculate the initial acceleration of the rocket, and the mass of the rocket is 5 times 10 to the 6 kilograms. Okay, we're gonna model this as a box because I want to do a free body diagram. So don't forget that the rocket has weight. So the force that they give us, which I will call, let's call it up thrust actually, not F. Let's call it up thrust to avoid confusion. So up thrust, this is the 7.3 times 10 to the 7 newtons that they mentioned. Okay, and they give us the acceleration. No, they don't give us the acceleration. We have to calculate the acceleration. Okay, the acceleration is going to be upwards, okay, because it moves up. So the sum of all forces, the resultant force, is equal to ma, right? And the resultant force is up thrust minus m times g, and this is equal to ma. And we are interested in the acceleration, so the acceleration is going to be up thrust over m minus g. Okay, so the up thrust is 7.3 times 10 to the 7, and then we have to divide by the mass, which is 5 times 10 to the 6, okay, minus 9.81. I'm being sloppy about the units. Actually, let me put the units in. So the units are newtons over kilograms, okay, minus 9.81. Newtons over kilograms is meters per second squared, okay? You can check for yourselves, and this is meters per second squared. So the final answer is 4.79 meters per second squared, which is about 4.8 meters per second squared. And to convince you, F is MA, right? If we use square brackets to denote the units of these quantities, we see that the Newton is equal to the kilogram times meters per second squared. So newtons per kilogram are equal to meters per second squared. Okay, so I hope this helps. Question B, give one reason why the acceleration will increase as the rocket rises. So the mass of the rocket decreases as the fuel burns. So the mass of the rocket decreases as the fuel burns. As the fuel burns. Okay, let's go to the back of the paper. Okay, with the thrust roughly unchanged. Okay, a smaller mass, okay, yields a larger acceleration. And we can see this from the formula we derived. So the acceleration is up thrust over mass minus g. Okay, so pretty much as the mass decreases, the acceleration increases if u is approximately constant. Okay, and it's constant because as far as fuel is burned, right, you will have an upthrust which is going to be approximately constant. It's not that more fuel will give you more upthrust. This is what I'm trying to say. Okay, let's move on to the next question, question 12. Okay, question 12. A teacher demonstrated the principle of conservation of linear momentum using two gliders A and B and an air track. A has the same mass as B. A and B were initially stationary, then A was pushed gently towards B as shown. State the principle of conservation of linear momentum. So, okay, in a closed system, and closed means a system that is not disturbed by external forces, okay? So a closed system will be, I don't know, your pen sitting on your desk, okay? It's not affected by, I mean, you're not pushing it around. If you push it around, it's not a closed system anymore. So in a closed system, and in the absence of external forces, okay, the total momentum, the total P, let's call it PI, before a collision, before a collision equals the total momentum, let's use a clean page, the total momentum PF after the collision. Okay. B. A magnet was attached to each glider. The gliders collided and stuck together. A data logger and sensor were used to record the velocity of A. The velocity recorded after the collision was half the velocity recorded before the collision. Deduce whether these results show that the law of conservation of linear momentum is obeyed. So basically, the situation here is that we have mass times v, because both objects have the same mass. So before the collision, we have, so this is the momentum of object A before the collision plus 0. That's the momentum of glider B, okay, because it's stationary. And this is equal to m plus m times v over 2, okay? So this yields m times v is equal to m times v, okay? So this is your PI and this is your PF, since they have the same mass. So you can write that momentum is conserved, okay? Since the mass, let's go to the clean page behind, okay? So this is a double asterisk, this is a simple asterisk, okay? So this is the simple asterisk, and here is the continuation of question B part 1, okay? So momentum is conserved since the mass, did we write? Yeah, since the mass doubles, thus the velocity, thus v halves. And v is the velocity after the collision, okay? So yeah, momentum is conserved. Okay, part 2, explain why the force of attraction between the two magnets did not affect this demonstration. So if you put a magnet here and a magnet there, so magnet B will attract A to the left, and magnet A will attract B, to the right, and magnet A will attract B to the left. So the force is the same pretty much, okay? Because magnetic forces, just like electric forces, like the Coulomb force, for example, these are Newton's third law pairs, okay? Same magnitude, opposite direction, two different objects. So this is Newton's third law pair. So they cancel out pretty much. So momentum is still conserved. So the force, let's write it in words. So the force on A, okay, and the force on B, okay, are equal in size, okay, and opposite in direction, okay. So they are a Newton's third law pair. Okay, so N3 means Newton's third law. Again, now we will need extra space again, so I'm gonna make 3 asterisks now. So we continue here, okay, I guess it's clear. So these forces, so actually let's write it. So these magnetic forces are internal forces, okay. They cancel out, okay, because they are equal and opposite. So they don't change the momentum of the system. Okay, so we can write as a supplement that only external forces, for example, if you push it, if you put your finger during the collision or something like that, that will prevent momentum from being conserved. So only external forces can change the conservation of momentum. I hope this makes sense. Okay, my handwriting is regressing again. Okay, I do my best, guys. So of momentum. All right. I don't know if I ever mentioned it, but my handwriting was horrible since I was a child. Because when I was really young, like first year of elementary school, second year, I was a really bad student and I was behind my class because I went to school younger, because the rules were like that. So I remember it actually because it was so uncomfortable. I wasn't able to learn, and so handwriting had to go. I mean, I didn't really make an effort to improve my handwriting because I was struggling to understand the harder classes for me at the time, so language, math, etc. So yes, as a kid, I was not really a good student, but I improved later. So towards the end of elementary school and then in high school, etc., and even in graduate school, I was a really good student, or at least on paper, because I still feel like there are many things to learn and stuff. So anyway, let's move on to question 13. Okay, question 13. Tennis players can practice using a tennis ball machine. The machine projects tennis balls horizontally from a height of 2.54 meters as shown. Okay, question A. Show that the time taken for a ball to reach the ground is about 0.7 seconds. And short story from my life. So when I was a professor at a small college in Illinois, they had this machine, and I asked the operator to shoot a tennis ball towards me. I played tennis when I was younger, a little bit. I'm not good at it, so I asked him to make the machine shoot at me at the same speed Roger Federer, for example, serves the ball, and I couldn't even see it. Okay, I didn't even see the ball. So yeah, it's crazy. It's crazy that they can do these things. I mean, the tennis players. Okay, so for question A, we're gonna use SUVAT. So the most appropriate equation is S is U times T plus 1/2 AT squared, but we will use it in the Y direction, right? So let's call it Y. So this is the Y direction, okay? Y is, the initial velocity in the Y direction is 0. So we just have 1/2 GT squared, which means that we can solve for T. So 2y over g is T squared. So T is the square root of 2y over g, so the square root of 2 times 2.54 over 9.81, which yields 0.72 seconds, okay, which is very close to 0.7 seconds that they ask. So success. Question 2. The ball lands on the ground at a horizontal distance of 17.89 meters from the machine. Calculate the velocity of the ball as it is projected from the machine. So we're going to use the same SWOT because it works. Let me know if you use something else. So S is U times T plus 1/2 AT squared, but now we're going to apply it in the X direction, okay? So X is ux, the x component of the velocity, because in the beginning the ball only has a horizontal component ux, it doesn't have a uy, okay? So ux times t. There's no acceleration in the x direction because they don't mention anything about air resistance, for example. They never do, actually. So at the A level, level of physics, if that makes any sense, they don't give you, complicated problems like that. So all we have to do is to solve for ux. So ux is x over t. X is 17.89, time is 0.72. So this yields 24.86 meters per second, okay, which is close to 25 meters per second, for example. Okay, moving on. B, the initial velocity of the ball as it is projected from the machine can be increased. Explain how increasing the initial velocity would affect the angle at which the ball hits the ground. So, okay, let's first state that the time of flight is the same, actually. So the time of flight is the same since t is the square root of 2y over g, right? So the height doesn't change, so the time doesn't change. Also, vy, when the ball hits the ground, also doesn't change, okay? And we can see this from the fact that v is u plus at. So vy is actually uy plus gt, but uy is 0. So vy is g times t. G is constant, t is constant in this case. So vy is constant, the y component of the velocity, okay? But vx is larger. Okay, and okay, let me fix this. So is larger, and we can, to find the angle with which it hits the floor, we can come here and recall that the velocity, okay, is tangent to the trajectory. Okay, so that's your v. Okay, but v has an x component, let's call it vx, and a y component, let's call it vy. Okay, and if this is our angle theta, right, we see that but vy is larger. Okay, therefore tangent of theta is equal to vy over vx. I hope this is clear. You can see it from the scheme. Okay, so the y component has to be divided by the x component to find the tangent of theta. So as vx increases, tangent of theta decreases, thus theta also decreases. Okay, so the angle is going to be smaller, the angle with which it hits the floor. So it's not going to be sharp like that, it's going to be shallow. Okay, so something like that. So your angle will be that one. So that's your theta. Okay, I hope this makes sense. And let's move on to question number 14. Okay, question 14. A student exercises by lifting weights attached to a machine. The machine has a cable as shown in the photograph. The cable passes through a handle and is connected to a weight. I have to say at this point that I'm totally against using machines to exercise. I feel like they force your body into non-natural positions, unnatural positions. Okay, I mean, that's the proper word to use. And you get injuries. So to exercise, I always prefer to do a sport. So boxing, for example, climbing. If you want to gain muscle, for example, you can box, you can climb. Or if you want to create stamina, just run. Why run in I don't know, in a treadmill, for example? So, but anyway, let's move on. That's just me, and I'm quirky, so whatever. So there is a tension T in the cable. The angle between the two sides of the cable is 60 degrees as shown in the diagram. A person keeps the cable stationary by applying a force F of 121 newtons. Determine the magnitude of the tension T in the cable using a scaled vector diagram. So, okay, this is one of the problems that I always hate because I have to use this ruler. Okay, so let's set the rule that 1 centimeter is 10 newtons, which means that we need 12.1 centimeters. So 12.1, okay, great. It's not perfect, but it works for now. So this is going to be our force F, okay, which is 121 newtons. Now to add the two tensions, let me show you something that will help. So I'm gonna take this and create a clean page. Okay, so these are the tension vectors. So this one and this one. Okay, and they are equal and they make an angle of 60 degrees. To add them up, we have to, in a vector diagram, before we add them here in the diagram that we are trying to make. Okay, so to add them up, you have to parallel transport this one to the head of the other one. Okay, I hope this makes sense. So okay, so we have to parallel transport the vector t. Okay, now this angle is 120 degrees. Why is that? Because if we extend these lines to help us see, we can use Thales' principle to see that this angle is 60 degrees, just like this angle. Okay, so the angle between the two vectors is 120 degrees, not 60. Okay, I hope this is clear, and this is the trick actually, because now you can add them up very easily, because F is going to be this vector, right? That connects them. Because the forces are balanced, you have to finally end up with a closed diagram. Okay, so this is what we will go here and do. Okay, I have to bring the ruler up, unfortunately, again. So, okay, let me go back here again. Sorry. So if that angle is 120 degrees, then these angles are 30 degrees. Okay, so that's the other thing. And they are 30 degrees because this is an isosceles triangle since t, the two t's are equal, right? So let's bring the ruler up. Okay, so the ruler also measures angles, but okay, this is going to be difficult, guys. Okay, 24, so it has to be 54, right? So 54. I'm sorry, I'm trying. Okay, 50. What happened to that? Okay. Okay, so let's use red. So, okay, I drew a line. And then if we go here, this angle has to be 24 minus 30, so 174. Jesus, this is difficult. Okay, it's approximately that. Okay, so I hope you understood what I tried to do. So now this angle is 30, this angle is 30, and this is 120. And these two vectors have to be equal. Okay, let's erase the extensions. Okay, so I hope you understood what I tried to do. So this is your t, and this is your other t, and we still have this leftover line. Okay, great. And I have to bring the ruler up again to measure this side. Okay, so it seems like it's 6.9, and this should be 6.9 as well, the other line. Okay, yes, so it's 6.9, maybe 7. So let's take it, let's make it 7, and we will call t as being equal to approximately 70 newtons. Okay, this took a little bit of work, but I hope it was understandable. The key here is this this realization that the angle between the two vectors is 120, not 60. Okay, so okay, let's move on to part B. The cable is attached to a 150 newtons weight. Each time the person pulls the handle, the weight moves up a vertical distance of 0.25 meters. The weight returns to its original position when the handle is released. The person exercises by pulling and releasing the handle. They do this 90 times in 120 seconds. The exercise machine displays the average power of the person as 35 watts. Deduce whether the power displayed by the machine is consistent with the data. Okay, so power is work done over time. Okay, so in this case, the work done is equal to the force times the distance delta y, which they give us as 0.25 meters, so that's your delta y over time. And this is done 90 times, so you have to multiply this 90 times. Okay, so I hope this is clear. So 90 times the force used, 150 times the distance, 0.25. So the units are newtons times meters, which make what kind of unit? Let me know in the comments, pause the video and write it down. Okay, and I'm going to show you in a moment. And this has to be divided by the total time, which is 120 seconds. So newtons times meters makes joules. Joules over seconds make watts. Okay, and this is 28.1 watts, which is, less than 35 watts. So not accurate. So not accurate. Okay, this was question 14. We are ready to move on to the next question. Okay, question 15. The photograph shows a ladder that a person can use to climb into the roof space of a building. Okay, this looks interesting. I've never seen this before in my life. When not in use, the ladder is stored in the roof space and the opening to the roof space is covered by a board. The board is hinged to the ceiling at one end. The ladder is attached to the board by a rail as shown below. A small block prevents the board from rotating into the roof space. Okay, state what is meant by the center of gravity of an object. So it's the point, the center of gravity is the point. So the point through which, okay, the entire weight of an object can be considered to act from. Okay, let's move on. Part B, the weight of the board and rail is 50 newtons. The weight acts at a distance of 0.45 meters from the hinge as shown. The total weight of the ladder is 2.7 meters with 0.85 meters to the left of the hinge. Okay, the weight of the ladder is 54 newtons. Assume the ladder is uniform. Explain why the board and ladder remain in the position shown. Okay, so we have the 50 newtons as they tell us, and they also tell us that this distance is 2.7 meters. Okay, so that's 2.7 meters. Therefore, the middle is going to be 1.35 meters. Okay, so the middle is going to be somewhere there, and it's to the right of the hinge, and that's where the 54 newtons act from, the 54 newtons being the weight of the ladder. Okay, so we have a clockwise moment, the 54 newtons, and an anti-clockwise moment, the 50 newtons, right? So let's first write that if the ladder is uniform, okay, the center of gravity, then the center of gravity, I wrote it as COG, okay, is at the center. Okay, so 2.7 over 2, which is 1.35 meters, comma, so 0.5 meters from the hinge. And how do we know this? Because this distance, let me use orange. So this distance, okay, is this distance, okay, is 1.35 meters. So you can immediately see that this is then, so we have 0.85 and 0.45. So this is 0.5 meters, okay, the distance from the hinge. Okay, so 1.35 minus 0.85 pretty much is 0.5. Okay, I'm gonna write it here. 1.35 minus 0.85 is 0.5. Okay, so the moments, so we have the clockwise moment is equal to 50, sorry, this is the clockwise moment. Okay, so the clockwise moment is 54 times 0.5, which yields 27 newtons. The anti-clockwise is 50 times 0.45, which is sorry, newtons times meters is the moment, the torque. Okay, so that's 22.5 newtons times meters. Okay, so we see that the clockwise moment is larger than the anti-clockwise. Okay, so the ladder is arranged as shown. So what I mean is that the ladder remains in that position because this moment is larger than the moment that wants to pull it in the other direction, so it stays up. pretty much. Okay. Part 2, a downward force is required to rotate the board away from the block. This force is applied 0.80 meters, 0.80 meters from the hinge. Determine the magnitude of this force. So this is going to be a force applied just right there. Oops, they said 0.8, so somewhere there. Okay, so this is the force we are looking to find, and it's 0.8 meters from the hinge. I hope this is understandable. So F times 0.8. So F is going to be an anti-clockwise moment, like the 50 newtons force. Okay, so F times 0.8 plus the anti-clockwise moment, okay, which is 22.5. Okay, is should be equal to the clockwise moment, which is 27. Okay, so F is 5.63 newtons, which is the answer. Okay, so this was problem 15. Let's move on to the next question. Okay, question 16. A steel object is held by an electromagnet. The magnetic force prevents the steel object from falling. A, state 2 reasons why the weight of the object and the force from the electromagnet are not a Newton third law pair. So, both forces act on the same object. Okay. But Newton's third law pairs require the forces to act on different objects. Okay, and the other reason is that they are different types of forces. Okay, because the weight is a gravitational force and the force from the electromagnet is a magnetic force. Okay, so they are different. B, the electromagnet is suspended from a support by a steel cable as shown. Question I, when the object is suspended, the strain in the cable is 3 times 10 to the negative 4. Calculate the Young modulus of the steel in the cable. Okay, so this requires a little bit of thought, because, okay, they give us the strain, they give us the cross-sectional area, they give us the unstretched length of the cable and the stiffness of the cable. Okay, so the strain is delta x over L, and using this we can find, using this formula, we can find delta x. Okay, we can find the extension pretty much. Okay, so delta x is strain times the length, so 3 times 10 to the negative 4 times 3.8 yields 1.14 times 10 to the negative 3 meters for delta x. Now we know that force is equal to the stiffness times delta x. Okay, so we have 2.8 times 10 to the 7 times, which is the force, right? Which is the stiffness of the cable, times delta x, which is 1.14 times 10 to the negative 3, yields the force, which is 31,920 newtons. Okay, and now we can use the fact that stress is strain times the Young modulus to find the Young modulus. So the Young modulus is stress over strain, so force over strain times cross-sectional area. Okay, because stress is force over cross-sectional area. So, okay, I'm going to use a clean page because everything is crammed together there. Okay, so 31,920 newtons over 3 times 10 to the negative 4 times 5.1 times 10 to the negative 4 meters squared. So this yields 2.09 times 10 to the 11 pascals. Okay, so we're done with part 1. Let's go to part 2 of this problem. The force extension graph for the steel cable is shown below. So the force, they show us the total weight of electromagnet and steel object force, okay. When the electromagnet is switched off, the steel object falls. A student states that the change in elastic strain energy stored in the cable will be transferred to the gravitational potential energy of the electromagnet. Discuss the student's statement. You should add to the force extension graph as part of your discussion. So the first thing we're going to write down is that the area is equal to the elastic strain energy, okay, stored, because it's we have force times extension, so newtons times meters is energy, okay. So when the object falls, okay, the cable is still stretched by the weight of the electromagnet. Okay, so let's call it okay. So this is the, let's say this is the weight of the electromagnet, okay. So this is going to be the new force on the cable, okay. So if we bring down a line, okay, and if we do the same with this line, okay, so this is the energy released. So, okay, I hope this makes sense. So when the object falls, the cable is still stretched by the weight of the electromagnet, okay? So the energy released is the energy under that trapezium. So energy released is equal to the area of trapezium. Okay, now comes the catch. So the gain, gain of electromagnet, so the gain in potential energy, gain in potential energy, gain in gravitational potential energy, sorry. So gain in GP for the electromagnet is mg times delta x, where delta x is this. Okay, so that's your delta x. But this is equal to the weight of the electromagnet times delta x. Okay, so this is this area, pretty much. Okay, the green area. So this is GP gained. And why is that? Because once the weight drops, the electromagnet, the cable is not going to be so stretched, so it's going to go a little bit up. And how up? It's going to be equal to that delta x, okay? Because now we removed one of the weights. So I hope this is clear. So we can immediately see that the elastic energy released is larger than the GP gained, okay? So the elastic energy gained, okay, is released, sorry, not gained, excuse me, released is larger than the GP gained, okay. So student is wrong, okay, because there's this leftover triangle, pretty much the leftover area of that triangle. Okay, so this was question 16. Let's move on to the next question. Okay, question 17. Scientists use weather balloons to carry equipment into the upper atmosphere to monitor weather conditions. The photograph shows a weather balloon. Okay, you see it, it's pretty. So upthrust acts on the balloon is released and accelerates upwards. State what is meant by upthrust. So upthrust is the density of air in this case times g times the displaced volume. So upthrust is an upward, so let's write it down more properly. So upthrust is an upwards force, okay, on an object, okay, equal to the weight, okay, we're gonna need extra space, to the weight of the displaced fluid. So in our case, in this problem here, air. Okay. B. When the balloon is released, the initial upward acceleration is 4.8 meters per second squared. Show that the weight of the balloon and equipment is about 13 newtons. The volume of balloon and equipment is 1.63 cubic meters, and the density of air at ground level is 1.23 kilograms per cubic meter. Okay, so I'm gonna draw it up here. So there are two forces acting on the balloon, as stated, the upthrust and the weight of the balloon plus equipment. So and the acceleration is upwards. Okay, so the resultant force must be equal to ma, and the resultant force points upwards. So upthrust minus weight is ma. Okay, so upthrust is m times g, which is the weight, plus ma, and we have to solve for m. So upthrust is m times g plus a. So the mass is equal to the upthrust over g plus the acceleration, and the upthrust is equal to the density of air times g times volume over g plus a. And now we can plug in numbers. This is what I do, by the way, for those of you who are watching my videos for a long time. I prefer to reach a final algebraic expression and before plugging in numbers. So 1.23 times 9.81 times 1.63 over 4.8 plus 9.81. This yields the mass as 1.35 kilograms. Okay, but this is not what they are asking, so I'm gonna put a double asterisk and go to the back to calculate the weight, which is m times g, so 13.2 newtons. Okay. Part 2. The graph shows how the density of air decreases with height above the ground. Okay. The scientists, what kind of curve is that? Let me know in the comments. Okay. And no, I'm not going to tell you, so just tell me. I'm curious. And also go check it out. And it's an interesting equation from physics outside the scope of what you need to know, but it's fun. So the scientists want to make measurements at a height of 25 kilograms where the balloon would stop rising. The balloon will expand as it rises and will burst if its volume exceeds 50 cubic meters. Deduce whether the balloon could support the equipment at a height of 25 kilograms without bursting. Okay, so at 25 kilograms, okay, so these are the 25 kilograms. So you see that the density, every little square in the density direction, in the y direction, so this little square, every little square is about 0.02 kilograms per cubic meter. So it's about 2.5. So we're going to estimate that at 25 kilometers, not kilograms, I'm sorry. Okay, the density is about 0.05 kilograms per cubic meter. So somewhere there. Okay, so let's calculate the upthrust. Is going to be the density of air times G times the maximum possible volume, which is 50. Okay, so 0.05 times 9.81 times 50 yields 4.5 newtons, which is larger than 13.1 newtons, which is the weight of balloon plus equipment. So this works. Okay. Equipment. Okay. Moving on to part C, a long writing problem with an asterisk. Okay, so 6 marks. Again, as I said in the beginning, the strategy is that you have to think about 6 separate sentences, so 6 separate statements to answer these types of questions. But in this case, we can get away with 4 actually, so that's okay. It happens sometimes. So a weather balloon made of a strong material will rise and eventually stop expanding. It will continue to rise until it reaches a maximum height. Explain how and why the velocity of the weather balloon changes from release until it reaches its maximum height. Ignore the effects of viscous drag force. So at release, okay, the upthrust is larger than the weight. So the resultant force is upward, okay, and balloon accelerates up, okay, with its velocity increasing. Okay, once the balloon reaches its maximum volume, okay, let's write it, okay, volume, it can no longer expand, okay, so as it rises, okay, air density decreases and upthrust also decreases. Okay, this continues until the upthrust becomes smaller than the weight. Okay, giving a resultant downward force. Okay, from that point, okay, the balloon decelerates, okay, and its velocity falls to 0 at the maximum height. Okay, and that's the answer. This is problem question 17. Let's move on to the last question, which is question 18. Okay, question 18. A student carried out an experiment using a data logger to record the motion of a ball bearing as it fell through a liquid. Question A, state the conditions under which Stokes' law applies to an object moving through a fluid. So we need small spherical objects, okay? And we need slow speeds, okay? So that the flow is laminar, okay, and not turbulent. Okay, B. The graph obtained by the student is shown below. Explain the shape of the graph. Okay, so the gradient of the displacement time graph is the velocity. So, okay, in the beginning, velocity is approximately 0. Then, what did I say? So the velocity is the gradient of the displacement time graph, right? Okay, so the velocity, you see that the gradient increases, but then at some point it's stationary, okay? So it reaches a terminal velocity, okay? So we're gonna write all these things down. So at the start, ball is stationary, okay? So the gradient is 0, okay? As the ball speeds up, okay, drag increases, okay? So the resultant force falls, okay? And the gradient's rate of change slows. I hope this makes sense. And the gradient's rate of change slows. I hope this makes sense, and we will have to move to a clean page. Okay, once drag balances balances weight minus upthrust, because recall as the ball is falling, let's do it right here. So let's do a free body diagram, I mean. So we have the weight, the drag, and the upthrust. So upthrust plus drag becomes equal to the weight, okay? So once the drag balances weight minus upthrust, okay? So what I mean is that drag is equal to weight minus upthrust for balance, okay? The ball reaches terminal velocity, and the gradient remains constant. Okay, part 2, the ball bearing had a diameter of 1.6 millimeters. The difference between the upthrust on the ball bearing and the weight of the ball bearing is 1.45 times 10 to the negative 4 newtons. Calculate the viscosity of the liquid. Assume that Stokes' law applies. Okay. So the drag force is 6 pi r times the viscosity times V terminal. So the viscosity that we need to find is, let me think, is drag over 6 pi. I'm gonna replace the radius with d over 2. So d over 2, because they give us the diameter. Okay, times V terminal. So drag over 3 pi d V terminal. Now let's find V terminal is the absolute value of the gradient, and the gradient is the absolute value of delta S over delta T. And we will use, from the graph, we will use the point where the displacement is this one. Okay, so we're gonna use these points to find. So this is your delta S and this is your delta T. So we will divide this by this to find the terminal velocity. Okay, so delta S over delta T is 7.5 times 10 to the negative 2 minus 0, okay, over, and you can check for yourselves that this point is 7.5 times 10 to the negative 2 meters, and then that delta t interval is 0.4, okay? And in fact, it's 0.8 minus 1.4 pretty much, which is equal to 7.5 times 10 to the negative 2 meters over 0.4 seconds, which yields 0.19 meters per second. And we will use another clean page. So eta, the viscosity, is equal to the drag, which is 1.45 times 10 to the negative 4 over 3 pi times 1.6 times 10 to the negative 3 times 0.19. This yields 0.05 pascals times seconds. And we find the pascals because in the numerator we have newtons, and then in the denominator we have meters times meters per second. So this is pascals and that's seconds, so pascals times seconds. Okay, took a little bit of work, but I hope this makes sense. Okay, and part 3 is the last question in this test. The student heated the liquid and repeated the experiment. The ball bearing took less time to fall a given distance in the liquid when the liquid was at a higher temperature. Explain why. Assume the density of the liquid is constant. So as the temperature increases, the viscosity decreases. Since the density, okay, is the same, okay, weight and upthrust are the same, okay. Since drag is equal to 6 pi eta r times v, okay, as eta decreases, v needs to increase so that upthrust plus drag is equal to the weight, okay. Thus v terminal occurs, and I'm gonna need extra space. Okay, so here is one asterisk and this is two asterisks. So this is the first asterisk and this is the second asterisk. Okay, so V terminal occurs at a higher speed. Okay, since V terminal increases, time to cover the same distance decreases. Okay, and this was Unit 1 from January 2023. It's already been almost 4 years. Time flies. I can't believe this. So anyway, let me know what you think about these videos. Hopefully my handwriting improved in this video. Thank you guys for watching. Please share it with your friends. Please like and subscribe. 90% of people who watch these videos are not subscribed, and this does not help the channel grow because with more subscribers, YouTube pushes your material more. So I want this channel to grow and hopefully make it into a full-time job if possible. So anyway, thank you guys for watching. See you in the next video. Bye.